Hi, welcome back. So today we will be still looking at chapter 23. Today's main topic will be electrical elements in alternating current circuits. Okay, so we'll be talking about resistors, inductor, and capacitors. Those three elements, how they behave in AC circuits. So let's jump in. First, we'll start with the simple element, the resistor. Um, and see how it behaves in the AC circuit. Okay, um, so the electric signal we get from sockets, they are AC signals. So that means the voltage alternating in positive regions and negative regions constantly from time to time. And then the rate of that change in the frequency is for what we are using is about 60 hertz. Okay, so you can write then the voltage as a function of time. That should be a sine function. If you prefer, you can also use a cosine function, but it will have a peak value in that case. So if you have the voltage applied to a resistor like this, then the voltage across the resistor is also this function similar to a sine function, but voltage on resistor would have a peak and then sine of omega t. Omega is the angular frequency and t is the time variable. So omega will be 2 pi times f. According to Ohm's law, so then for a resistor, voltage is equal to the current times the resistance. So then the current is the voltage divided by the resistance. So if we take this expression in place of voltage on the resistor, V sub R means voltage on the resistor, it will have peak value sine of omega t and then divided by R. So in that case, you get a peak current, which is V voltage peak over resistance, okay? And then the sine function will follow that. So then in this case, you can see if you have a resistor in the AC circuit, then voltage is a sine function, current is also the same sine function follows, okay? So, and if we calculate for the power consumed by this resistor, we can use I squared times R, which I is the sine function that we saw earlier, the peak times sine or omega t. So if you square the expression, you get I peak square and then sine square omega t, and then times R. Okay, so this is just switching order a little bit, but I peak square R sine square omega t. And for the average power consumed by this resistor, so it's the average of this expression, I peak will be a constant number, so a square of it will be constant, and then R is a constant. Sine of square omega t will be varying over here. So then the average of power should be just the average of the sine square omega t average. Okay, so if you square the sine function, it will be something look like this. Okay, because you squared it, so it's all positive. And average of that will be just half of it from the middle here. So it varies from 0 to 1. So then half of that will be just 1/2. So then it's 1/2 of I squared peak R. That gives you that. But 1/2 of peak square value of current, last time we talked about, so that will give you actually the root mean square quantity of it and square. Okay, so then you can see the average power consumed for the resistor is then the RMS current square times R, okay, on that resistor. If we look at another expression for power, power could also be V square over R. V would be the V peak sine omega t. So then power will be V square peak over R sine square omega t. Again, if we calculate for the average of that, V square peak over R will be constant. The average will be on the sine square omega t, and sine omega square t will be average of that will be 1/2. Okay, just as the same as the previous slide showed. So then power average will be 1/2 V peak square over R, and then again peak square of the quantity, half of it will be equal to the root mean square of that quantity square. Okay, so then P power average would be, if you use RMS voltage, again, it will be voltage square over R. Now, you can also prove that if you use a third expression, calculating electrical power, power is V times I. So you take the same thing, and then if you square, or if you average, then at the end, you'll get the average power on the resistor will be then the RMS quantity of voltage times RMS quantity of I. Okay, so in this case, we can see that if you have a AC circuits, if the signal is AC, the alternating current signal to the element of resistor, then if you are calculating power, average power consumed on the resistor, it's similar to just a DC circuit, but in this time, you'll use the root mean square quantity instead of the just the value, the voltage or the current itself. Okay, so for DC, because voltage and current, they do not change, so you can use just the voltage and current. But for AC circuit, then instead of using just the actual value itself, we are using the root mean square quantity of those numbers to calculating the average powers. Okay, all right. So let's move on here. Now let's take a look on an inductor. If we have inductor in an AC signal, okay. So what happens here? Inductors are made of coils, and we learned earlier that if you have a coil there, once you have electricity going through that, if this electricity is varying, then the coil does not like the change of it according to Lenz's law, so it will oppose to that change. Okay, so AC, being an AC signal, that means it's always changing. So then there's always changing of current through this coil. So then you always get back EMF on this guy. So it's opposing the voltage added to that, the change of the voltage going through that. Okay, so let's say if you have voltage not applied to this guy, so there's back EMF on that. So the current, this is kind of like charging the inductor that we mentioned earlier, right? So if we are charging the inductor, the current actually goes from 0 up, right? So when you have V applied, then the current actually start from 0, small here. So let's say if you start with the peak voltage here, then the current will actually go up, and then it will peak later. So in this case, you can see if the voltage peaks first, then the current will peak later in about 1/4 of the period. So the period being 2 pi here. So then it is 2 pi divided by 4, which gives you pi over 2, which is equivalent to 90 in degrees. Okay. So in this case, we can see voltage will peak first, current will peak later. So it's lag of 90 degrees or pi over 2 in that case. And both of them will be a sinusoidal function. Okay, so either cosine or sine function, it's up to you to pick. So similarly, so that means in this case, if you apply voltage, then there's a response of the inductor to that, the current as a result of voltage applied. So we can write a similar version of Ohm's law in this for AC circuit for the inductor. So I, it will be equal to V divided by XL. So this is kind of resistance, but in this case, we call it inductance. Okay, so X sub L, that means the inductance or the reactance of the inductor to the voltage you apply. And it turns out mathematically, X in the inductance is equal to 2 pi times F times L, where 2 pi times F is omega, the angular frequency. Okay, so if you have frequency, you need to do 2 pi times the frequency and times L. L will be the inductance of the inductor. Okay, so this is called inductive reactance or inductance, or the yeah, my bad, sorry. It's just called the reactance, XL, inductive reactance. Okay, and then for the capacitor, it will be called capacitive reactance. All right. So then the current, RMS current and then RMS voltage are in relationship, just similar formed as the Ohm's law. So if your voltage is a sine function that you prefer to use, it has a peak times a sine function, then the current will be equal to the voltage, the constant number of peak value divided by this fixed number, also constant number, depending on your frequency, your peak frequency. Okay, so X or L, and a sine function in this case because as we saw earlier, the current peaks later, right? So if this guy peaks, that means sine of omega t is equal to 1, which omega t is 90 or pi over 2, or 90 plus 360 multiples of 360 or 2 pi over 2 plus multiples of 2 pi. So then if this is pi over 2, then this is 0, okay? And then another pi over 2 later, it will peak, okay? So then this is the expression for that, okay? So both sine function, but there's a shift of angle here in the argument, okay? So the phase shift there, that gives you its lag of the voltage by 90 or pi over 2, okay? All right, so let's take a look on this example. First example here says an inductor has a reactance of 100 ohms. I guess I forgot to mention about the inductance, the SI units for this guy, inductance, reactance, inductive reactance. So this is similar to resistance, so it has a SI units or ohms, okay? So let's take a look on this. So this one says it has a reactance of that. So inductor should be inductive reactance. Okay, so that means XL is given. So this is XL and this F. Okay, this guy is F, this guy is XL. It's asking you what's the inductance. It's asking you for L. Okay, and then what's the reactance if you are having a different frequency. Okay, so we know that XL equals to 2 pi F times L. So if you have F changed, then XL will change as well. Okay, so let's take a look on this here. So we just learned that for inductance, inductive reactance. Okay, so this guy XL is 2 pi F times L. So it gives us XL and F we can calculate for L, okay, based on this equation. So L then is XL divided by 2 pi times F, okay, so in this case. So 100 ohms on the top here divided by 2 pi times 80 hertz, okay. So then we get actually 0.199 Henry for the inductance. The inductance should be in Henry, okay? So just this equation there and then figure that out straightforward, okay? All right, so that's part A. Now part B is asking you if your reactance, if your frequency changes to 160, then what will be your new reactance, okay? Now based on this, you can see if this guy doubles, this guy stays the same, so then this will be double, okay? So quickly we can say that XL, this time prime, then will be just equal to 2 pi or 2 times because F or you can just use the formula or whichever, okay? Doesn't really matter. So 2F, 2 pi times, now this time is 160 hertz, right? And then times 0.199 Henry. This should give you just twice of what we had earlier, so 200 ohms, okay? So that's the new inductive reactance on that, okay? Or you can just simply say because your frequency doubles, so this guy will be two times of the original one will be 200, so either way. Okay, so let's go back to the slide there. Now let's take a look on what's the power consumed on the inductor when it's in the AC circuit, right? So the power we can do voltage times I. Use our normal expression or one of the three expression there. And V is a sine function, and then peak value. So this is a cosine function because it was originally I is I as a function of t is a peak value, right? Which is V peak over XL, but we can just use I peak, then sine of 90 minus omega t, okay? And sine of 90 minus omega t actually is cosine, okay? So it's actually cosine of that. So that becomes that. All right. And then I think we have seen this a couple of times. So this is constant, this is constant. So these two can stay together, and then we'll just put these two together. Sine of omega t times cosine omega t. So for one of the trigonometry entities, right, sine theta cosine theta actually is equal to 1/2 of sine 2 theta. Okay, so then that gives you sine of 2 times omega t is the theta, and then 1/2 there. Okay, so now this becomes also a sine of 2 times omega t. Okay, there. And then the average, if you do average, so these are all constant values. So 1/2 is constant, peak voltage is constant, peak current is all constant. Then you are just averaging this sine function. Okay, so sine function, as we know, half of the time is positive, half of the time is negative. So average of that would be actually 0. Okay, so this gives you the conclusion that average power consumed by the inductor is actually 0, right? So surprisingly, but this is actually a good news. So that means it does not consume any power, okay? So if you have an inductor in an AC circuit, it merely just store power in the form of magnetic field, right? So all we learned before, if you have an inductor current going through, then you actually store energy in the form of magnetic field, okay? So then therefore, it does not consume any power, okay? So great. All right. So now let's move on to capacitors. So if you have a capacitor in the AC circuit right now, okay, so now this is like charging of the capacitor, right? So if this is charging in the charging process, we know that for the charging process, the capacitor, actually the current peaks, right? The current starts from maximum and then goes down. And then the voltage on the capacitor actually start to build up, right? Because Q, the charge is building up, so the V is building up. So you can see that actually in this scenario, then it's the other way around, that current actually peaks first, then voltage peaks later, okay? But anyway, this is when you apply voltage, right? So to this capacitor, so and then the current is changing as a result. So then similarly, we can set things up like to get the Ohm's law, but this time we'll take the approach differently. We'll look at the voltage, okay, on the capacitor, which is related to the charge on it, and then times this constant number of capacitance. And we know that current is actually equal to change of charge over change of time t. So Q is C times V, but C is constant number, so then it's change of voltage over change of time t. Now, if we have voltage as a sine function, then change of that over change of t, then it's actually slope of that sine function at any given point. And then if you know the trigonometry functions well, change of slope of sine function actually gives you a cosine function, okay? Which in this case would be for the current, it's going to be if you do change of voltage over change time t. So then VC peak will stay, and then C comes from here, omega comes from doing the slope of making the slope of sine function out of there, and it becomes a cosine function, okay? And cosine function could also be written as omega t plus pi over 2, because in this case, actually, your current peaks first, okay? So then we use this expression. So when this is 0, it's actually a peak value of sine of 2 pi, okay? And then your voltage will peak later by pi over 2, which is 90 degrees. And then this is exactly 1/4 of the cycle of the sine function or cosine function. Okay. So similarly, we can write that current is responding to the voltage applied as V over XC, where XC is called the capacitive reactance, and then it should have a SI units of ohms. This is then the similar version of Ohm's law in AC circuit for the capacitor. Okay, so this is for the RMS current and then RMS voltage as well. XC, it turns out to be 1 over 2 pi F times C. Or if you just write omega as 2 pi times F, then it's 1 over omega C. Okay, and in this case, we can see now your capacitive reactance are actually inversely proportional to frequency. Okay, for your inductor, its inductive reactance actually is proportional to the frequency. Okay, so this is the other way around. Okay, so inductors and capacitors, in many cases, they are opposite to each other. Okay. And now if we look at the power consumed by the inductor or by the capacitor this time, we can start with power equal to V times I, but this is on the capacitor, so V sub C times I. V is a sine function, peak times the sine omega t. I is peak value of I times the cosine omega t. Okay, so again, the two constants value of V peak and I peak can come out first, and then sine omega t cosine omega t will be 1/2 of sine 2 omega t, just as we saw earlier for the inductor. And if you do average of power, so average of sine function, again, half of time is positive and then half of time is negative. So average value of that will be 0. Okay, so this also tells you that for inductor or the capacitor in the AC circuit, it does not consume any power, electrical power. So it actually stores energy. Okay, and in this case, it will be in energy in the form of the electric field. Okay, so this is a capacitor. All right. So let's take a look on this example here. So it says the capacitor, you have the capacitor. So this is C. Okay, so this is C of your capacitor. This is C of your capacitor. And then now you have AC circuit, okay, AC generator, AC power source. RMS voltage, so this guy's RMS, okay, RMS V, so VRMS. And frequency, okay, so this is F, okay, F there. It's asking you what's the RMS current, because in A, you're looking for IRMS. So if you are looking for IRMS, then it will be VRMS over X. C in this case, because it's a capacitor, okay? And then B, it says if you wish to increase this IRMS, you can put a second capacitor in series or parallel, okay? So if you want to increase this guy, that means you want to decrease your XL or XC. Now for capacitors, if you have two of them, you can put them in series or you can put them in parallel, right? So which configuration will give you smaller XC? Given that XC, we just learned that XC should be equal to 1 over 2 pi F times C. So that means this CEQ of the combination actually has to be bigger, okay? So for capacitors, you need to put them parallel to add up, okay? So if you don't remember, but that's what you should have, okay? So then we should do that, put them parallel, okay? So then we'll find out that later, okay? Let's solve this one then. Let me just scroll it down there, okay? So we are looking for RMS current in A. So we know V, so I RMS should be equal to V RMS over XC. Okay, so in this case, XC XC is actually equals to 1 over 2 pi FC. Okay, so then we can do that. So if we put that in here, so it's over this whole thing. So that means it will be 2 pi FC times V RMS. Okay, so we do 2 pi, F is 60 Hertz. If you keep everything in SI unit, okay, and then C is 22 micro times 10 to the minus 6, okay, and then VRMS is 18, okay, so that will give you as the current 0.979 amps, okay, and because IRMS is equal to 2 pi FCV RMS, okay, so then if you want to increase this current, then this new C will be need to be larger. So let's call this CEQ. Okay, so CEQ should be larger. So CEQ then has to be larger, which means you put them in parallel. So then you do C1 plus C2. Okay. Now it tells you this new IMS is 1.5. Okay, so then we can calculate this CEQ, right? So then let's say this guy should be in parallel first. Okay, that's the answer for B. But in C, then we can calculate this new CEQ. So based on that, CEQ should be equal to then the I new RMS over 2 pi F times VRMS. Okay, so then we can calculate for how much this will be. The new current is 1.5 amps, 2 pi, 60, and 118. Okay. So that will give us, in this case, 3, or maybe I can write it down here. It's 3.372 times 10 to the minus 5. And this should be in farad. And we can convert it into microfarad, should be 33.72 microfarad. Okay. So the original C1 plus C2 is equal to this guy. So that means that the second one you need will be this CEQ minus C1, right? So it will be 33.72 microfarad minus the 22.0 microfarad. So that will be 11.7 microfarad at the end. Okay. 11.7, okay, microfarad. All right, so I think that's the full solution for this one. All right, so let's go back. So let's take a quick look on what we learned today. So we actually basically we look at the 3 common electrical elements in the AC circuits. Resistor just behave similar to its behavior in the DC circuit, but for the inductor, so then similarly, you just have the inductance, the reactive inductive reactance of that which is XL, that's 2 pi F times the inductance. Okay, so it's proportional to frequency. So the higher frequency, the more reactance of that will be. For the capacitor, it's the other way around. It's inverse of 2 pi F times C. So that means higher frequency, lower reactance of that. Okay. for both elements, they do not consume any power in the AC circuit. That's good. So that means they're just storing units for the energy. So if you have L that if you have frequencies very small, that means this value will be very small, XL. Okay, so XL is then actually kind of like just a wire in the DC circuit. DC circuit F equal to 0, right? Frequency equal to 0. So then it's kind of the straight wire. But for higher frequency, then the capacitor it's having 0 reactance, so it behaves like just like a straight wire in that case. Okay. So that will be it for today. We'll see each other next time. Okay. Bye.